Hi, friends. Mr. Rogers here, and today I want to do a quick little um, notes on polar and nonpolar, and then we're gonna do some polar and nonpolar practice. And so, let's start with just a Venn diagram. Everyone's familiar with Venn diagrams, and so I want you to draw one of these in your notes. And so we have the polar side here, non-polar side over here. So let's start with polar. So polar things have a charge. Since they have a charge, they are attracted to other items with a charge. So awesome. So those are the first two big ones. And we have to remember about these things, okay? So polar has a charge and it's attracted to other items with a charge. All right. Good start. So let's try something else here. Let's say oxygen and nitrogen are most common in polar items. So what I'm saying here is when you look at something, a molecule, and it has oxygen and nitrogen, there's a really good chance that it's polar. And what we're trying to look for is we need a close to an equal amount of oxygen and nitrogen compared to carbon. And so we're going to talk about this in a second, okay? But we need to have a close amount of oxygen and nitrogen to carbon for it to be polar. So for example, if I have 10 carbons, for it to be a polar molecule, I'm probably going to need somewhere around 10-ish. It doesn't have to be exactly 10-ish oxygen and nitrogen atoms for it to be polar. The other big thing is we always look for ends are most likely to be polar. So polar things have ends that typically are the ones that hold the charge. And so they're the ones that are the most polar. So the ends of a molecule. So if you think about it, if you were a molecule, your hands would be the areas that we're looking at and feet to see if you're polar or not. Because those are the things that are sticking out, and those are the things that are interacting with other things. And same with a molecule. These parts that stick out are the things that we're going to look for and see if they are polar. Next, we have nonpolar. So nonpolar, especially what we're going to be doing this week, nonpolar are a ton of carbons and hydrogens. Okay, you're looking for a bunch of carbons and hydrogens for nonpolar things. If we're going to identify, that's what it's going to basically be. Okay. Next, we are going to have, let's see here. This is, I guess we could just go opposite polar. This has no charge, and it's attracted to other items with no charge. Now, to be honest with you, they're not so much attracted to other things with no charge. They're kind of forced to be. The idea here is water likes things that are polar. And if you are non-polar, you are kind of relegated to only be able to talk to non-polar things. Non-polar things actually have no problem with polar things at all. No problem whatsoever. But they're kind of held to a different standard than polar things with water, and water wants nothing to do with them. Okay. All right. And then non-polar, one last thing here is we're going to say it's hydrophobic. Now, I forgot to put that over here. We can add this one over here. Polar things are hydrophilic. Okay. Water, obviously, is what hydro is. Phobic, I think you're familiar with phobic. Phobic means scared or has a fear of. So non-polar things are hydrophobic. They do not like water. Hydrophilic things, hydro philic. Philic means like in Latin. The other more common way of using philic is phile. So hydrophilic is water liking. Hydrophobic, water hating or fearing. Cool. Now, we're going to add one more big thing because this is going to kind of help us. Polar things are carbohydrates and nucleic acids like DNA. We're going to talk about those things this week. And nonpolar things are like lipids, or the more famous name for lipids that you guys probably are more familiar with is fats. Okay, polar, nonpolar. Now it's a Venn diagram, so we got to put something in the middle here. So let's put something in the middle. They are both organic molecules. So even though if you're polar, you could still be an organic molecule, or if you're non-polar. Cool. They are both important to life. Just because you're non-polar does not mean you're not important to life. And importantly, the last macromolecule here, proteins. Proteins can be both polar or non-polar, depending on what kind of protein it is. Carbohydrates and nucleic acids are always polar. Lipids are always non-polar. Proteins can be one or the other. So we have that down. We're going to do something called, we're going to do this all in one video. We're going to do something called polarity practice. And so we're going to go to the next slide here. It says polar objects have many oxygens and nitrogens. Think equal number of oxygens and carbons-ish. So I'll show you guys an example of this in a couple minutes. And non-polar objects have little to no oxygens. Think a bunch of carbons and very little oxygens. Not just carbons, I would also add and hydrogens. Okay. Now, we're going to go through a set of molecules. I only have like 6 or 7 here. And I want us to determine in our head if they are polar or non-polar. Okay, polar or non-polar. And so I'll show you a couple. The first 2 we're going to use as just examples, and then the other ones we're going to use as practice. Okay, so look at this molecule real quick and come to an idea. Do you guys think this guy is polar or non-polar? So this is a polar molecule. This is actually a molecule we've been talking a lot about. I'm hoping you recognize right away. It's H2O, so this is water. And we already knew water was polar. So here, the hydrogens are positive, the oxygen is negative. They have charges. This is a polar molecule. Let's try a different one here. Let's try this guy. So this is ethane. If we go back to here, it says polar objects have many oxygens and nitrogens. Non-polar objects have little to no oxygens. So right here, I have 2 carbons and 6 hydrogens. This is a non-polar item. There's no oxygens or nitrogens here. This is non-polar. This is ethane. Okay, this is ethane that we can use to, well, for a bunch of different reasons, but maybe a bunch of different things. Glucose is the next one. Take a look at it. So glucose, we're starting to get into bigger molecules. It gets harder and harder to see what's going on. And so let's actually count these up. We can always count. So we have 1 carbon here, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon. How many oxygens do I have? 1, 2, 3, 4, 5, 6. And so if we go back to our rules, we can see that polar objects have many oxygens and nitrogens. Think equal number of oxygens and carbons. This guy has the same amount of carbons and oxygens, plus there's just a lot of oxygens here. And like I said, they stick out on the edges. This is a polar item. This is polar. Glucose is polar. Also, we're going to find out that glucose is a carbohydrate this week. Carbohydrates are always polar. All right, next one. So this is 2 different two different molecules, but they're both waxes. Okay, and taking a look here, we have a lot of carbons on this guy and a lot of H's, a lot of carbons on this guy and a lot of H's, and I don't see an oxygen or nitrogen anywhere at all. So this would be non-polar. It's a non-polar item. This one's going to be a little bit harder. Let's take a look at here. So right off the bat, people always see the oxygens. They stick out like crazy, right? There's two red oxygens. But if we actually look at the actual whole molecule, we'll find out that we have two oxygens, okay? But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20-ish carbons and two oxygens. That kind of falls more under, you have a bunch of carbons and hydrogens and very little oxygens. So this is non-polar. This is testosterone. This is the secondary sex hormone of males. And you can see right away that even with the oxygens, there's still so many carbons, okay? Side note, fun fact, testosterone is a steroid. Steroids always have 4 rings. What I mean by rings is you can see there's a carbon ring here, carbon ring here, a carbon ring here, and a carbon ring here. There's always 4 in steroids, and steroids are lipids. They are fats. And so this is a non-polar molecule. Just like these waxes, these are both lipids too. These guys hate water, or water hates them, however you want to look at it. All right, last one. All right, so let's count up some things here. Let's count up the carbons first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's count up our oxygens. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're almost the same amount of carbons and oxygens. They're close-ish. Okay, close-ish. And we have oxygen, especially on the outside here. This is a polar molecule. This is polar. This is going to be lactose. So this is what people struggle to break down if they are lactose intolerant. Why they struggle to break it down is your body is supposed to cut this in half to be able to use it. And the thing that cuts it in half is an enzyme called lactase. People that can't eat lactose don't make lactase, and so this molecule never breaks down. And when your body doesn't break down something correctly, it panics, and so it has to get out of your body somehow. And so there's only 2 ways to do that. Once it's in your stomach, and you guys can both imagine those 2 ways. So I know I kind of went through the answers already. I wasn't planning to, but I think that's okay. I mean, I really want you guys to start looking at molecules and thinking to yourself, is that polar or is that non-polar? That's the point of this. I'm not really going to hit you that hard with this. It's more of an AP Bio college thing, but I do want you guys to recognize, okay, there's the same amount of oxygen, same amount of carbons. This thing is polar. Therefore, it's going to really like water. Oh, this thing has a bunch of carbons, a bunch of hydrogens, no oxygens, no nitrogens. This thing is going to hate water. It's hydrophobic. Okay? So when you look at molecules, start thinking about, will it or won't it like water, or will it like water? And also, is it polar or non-polar? I hope that helps. I hope that makes sense. If you need help, let me know.